Morning.
Good morning.
So, going to the compounds. Now, see what's next. We did periodicity, right? What did we do last? Trying to think. I am disoriented today. Normally I know, but it's not sure what we did last. What was our last thing we did? Do you remember? I think it was periodicity. Yeah. Yeah, I think so. This was it. Yep, periodicity. So I'm going to go ahead and open the periodic table. Bonus for all of you. And number 30. Okay, let's save. All right, that one's open. And I'll open the extra bonus because it's longer. And I'll give you a little bit longer for that one. All right, save. And that's it. All right. Okay, so last time I do believe, correct me if I'm wrong, we looked at periodicity, right? And that was the 5 different trends in the periodic table. And today we're going to look at electron configuration, which can be a little bit scary for some people, but don't be scared. It's not that bad. Let me see. I'm going to share my screen. Yep. Okay. Here we go. I'm going to screen share. Oh, there's go. Somebody just came in. Okay. There we go. All right. So looking at the next part, which is periodic electron configuration. So right here, we're going to look at this PowerPoint. Electron configurations are basically a way of knowing which orbital and which level each electron is in. that is in an atom. So basically, it's like the address of every person, you know, in the room, in the house. It's kind of what it would be, kind of like this one's in this room, this one's in that room, this one's in, you know, like that. And there's a few rules to follow when looking at electron configuration, and that's what we're going to talk about. But let's focus on this diagram right here. The very first thing you need to know is that there's 4 different types of orbitals, and types of orbitals doesn't mean they're levels. No, they're just types of orbitals. They're different shapes, they do different things. But let me annotate here, and this is kind of like a quick note to be taking. All right, so basically the orbital type, and then here it has a maximum number of electrons. So I'm just going to maximum electrons, number of orbitals, so number of orbitals right here like that. And let's see what else. Oh, tab one more. Where, oops, nope, not like that. I need to make it longer. Where does it begin? Okay, so begins. Okay, oops. No. Okay. Yeah, like that, begins. And the one last one is N, and you'll see what N is in a minute. Okay, so the very first one is our orbital named S. Maximum number of electrons it can have is 2. How many orbitals can it have? Are there an S? There's only 1, because every orbital can hold 2. Begins on period 1. And this is periods, by the way. And the N is also 1. So it's basically N. The N is N. I know it's weird. The N is, okay, let's just call it coefficient instead of N, because that's just weird. Okay, how's that? That's better. Coefficient. All right, it's N. All right, next one. The next one is P, orbital type P. And there are maximum number of electrons is 6, which tells me that there are 3 orbitals. And it begins in period 2. Okay, and the coefficient is still N. All right, next one is D. D is 10. The orbitals, there's 5. It begins in period 3, but the coefficient actually begins in period 4. And there's where we're getting confused. The N minus 1 is the coefficient. So you'll see what we're talking about in a minute. The orbital next one is F. And it has 14 total electrons. And it has 7 orbitals. And the last thing, where does it begin? It begins in level 5. But the coefficient, no, sorry, levels. See, this is where it gets confusing. This is what I was telling you. It's actually level 6. The coefficient is N minus 2. So that's why it's weird to think about that one. All right. So, oops, N minus 2. Okay, there we go. All right. So this is a little table that you might want to copy, so you'll have it at all times. All right. So just remember these, S, P, D, F. And these are regions of the periodic table. Oh, and that we could probably add that too. Yeah, let's add that, because that'll help you understand it even better, I think. So what region of the periodic table are we in? Okay, so the region here is, this is groups 1 and 2. Groups 3 through 8. This is, what do we call these? I said 3 through 8, and I meant A's. Oh, you know what? Let's just put A with it because otherwise it'll get confusing. Into A. Yeah, and this is 3A through 3A to 8A. And then this one, and I'm just going to call them the B's, but basically 3B through 2B, right? So all the B's. So basically, officially is 3 through 12, right? The groups without the A or the B's. And then the last thing is the cutout. Oops, I got a period on that. And by the cutout, we mean the part that's below, that doesn't have anything. And you'll see why it's called a cutout. Okay, there, that'll help you locate each one too. Once we go to the periodic table, you'll see. All right, so this diagram right here shows you everything that I just wrote right here. Okay, you notice that level 1 is where the 1s begins. You see that? So that begins here. Oops, let me get my spotlight so you can see it. Okay. Okay. So the spotlight right here, see how it's 1s? See, that's the first s. It begins in 1. There is one orbital, that's one box, which has maximum of 2 electrons, because that's how many each orbital can hold. All right. The next one is P. See how it starts with 2P? Okay. 2P. And we're saying that it begins with 2. See, there's the P's. It has a maximum of 6 electrons, so each one of these can hold 2. So that's 6. That's 3 orbitals. And the coefficient's n. N because we're level 2 and we're still calling ourselves 2. Okay? So we're in electron level 2. Now, this is where it gets a little confusing and is where I lose most people. But basically, on D, we start really on level 4. So after the 4s, you have the 3D. You see that? Okay, so the 3D is n minus 1. So the level is 4, but n minus 1 gives you the coefficient. So n minus 1 is 3. So it starts on really on 3, right? With 3. Not on 3, but with 3. And then level 5, oh, and then you got 4p and all that. Okay, so 5 right here. See, it's still an S, P, D. See, D is always one lower. That's what the n minus 1 stands for. And then F, this is their first F right here. We notice it says 4F, but we're really after the 6. That's why I say starts on 6. And you'll see what I'm talking about when we look at the periodic table, because it is one of those things that helps look at. But do copy this table right here, and we'll go to the periodic table next. Okay, so let's go. All right, so I need to get rid of this, sorry, or just move it. Can I move it? No, I cannot move it. Okay, so like I said, there are rules by which the electrons get filled. Oh, can I take you? Okay, can I take you off? I cannot just cut it out either. Okay, so it won't let me do that, I don't think. Nope. Text it. If I put a text, it'll just do a new one. Select. Oh, maybe I can select. Let me see. Okay, let's go back here and select. Select. Aha. I can move it now. There we go. I just want to move it out of the way so you can read everything. There we go. Now you can read it. We'll leave them there for now. Okay, so Pauli's exclusion principle is our first rule by which electrons get put into these orbitals. The first one says that no two electrons in the same atom can have the same set of 4 quantum numbers. So basically what it means that each of the boxes that we draw, and in my case, I don't draw boxes, I usually just do lines, only because when you're trying to do it fast, it's easier to do lines than boxes. And you'll see what I mean in a minute. Okay, so each orbital can only hold 2, but they have to be opposite spins. And the spin is a quantum number that we're not talking about quantum numbers, but basically there are 4 that describe every single electron in every single atom. And they are the principal, the magnetic, or as a model. Never remember the next one. I don't know what it is. I just cannot remember that third one. And then the last one is the spin. Okay, but this is the one that interests us, because these electrons are both in the same orbital. That means every single one of those other quantum numbers is the same except one, and that is the spin quantum number, which is what we have kind of represented by having one arrow going up and one arrow going down. So, okay, so that's that one. Let's go to the next one. Okay, can't do that. Do that. Okay, there we go. Let's go to the next one. All right, so Aufbau principle. That is another rule, and it says that every electron will occupy the lowest energy level first. Okay, there are a couple exceptions to this, but mainly, yes, this is followed to the T. All right. So what that means is, as you can see here, this is the energy, right? And you put them in 1s first. So if you have 3 electrons, they would go 1s, 2 in 1s, and 1 in 2s. If you have 5 electrons, then we go 2 here, and 1 in 2p. You see, because each time it goes up, up. If you have more than that, then just each one keeps filling in the level that it's at. So this diagram right here is very good for filling electrons. All right, the next one is the last one, Hund's rule. So this one is the one where it states that if there are orbitals of equal energy, which means that they are all in the same level and the same orbital type, so like S's or the P's or the D's, okay, they are each, this is what it says, they each occupy an orbital before doubling up. In other words, don't put them together, put them singly occupied and then double it. Okay, so like this. So if you were to follow this Hund's rule, would the right diagram or the left diagram be correct? Nobody? Based on the rule, what does it say?
I would think that it's the second one.
So the one on the right, okay? And you would be correct. See? That's because it says very clearly you cannot double up until you have each one of these filled, okay? So before pairing, you see that? Place 1 electron per orbital before pairing. So this is incorrect. So that's the next thing, is when we do our orbital diagrams, it'll ask you, is this right or is this wrong? Well, now you know. All right, so here's one. This is oxygen. We know oxygen has 8 electrons. Okay, so by what the rules say, right, we have 8 electrons. So if you look at the periodic table, and this is where I'm going to bring in the periodic table. Hold on. Let me escape this one and bring in the periodic table, because we need that thing in order to understand what I'm about to do. If we don't have a periodic table, it's almost lost on me. So let me go find the thing. I think I gave it to you up here. There it is, color periodic table. Okay. All right. So oxygen. And I'm still leaving that thing there so you can see it. So I'm just going to make it a little bit bigger so we can just look at oxygen. All right. And everybody else too, but I just want to be able to see everybody too. And there we go. There we go. That's better. All right. So according to the rule, what we need to do is we need to place the electrons in those orbitals, just like we said. All right, and remember this right here, and I'm about to highlight them all. So I think that's a highlighter, I think. All right, let's see. Let's make it yellow, I guess. Color? There's no color. Okay. Yeah, there's color. Yellow. There we go. Gonna make it yellow. Okay, so we're going to do these right here. This is your s orbitals. Okay, remember 1 and 2. See, that's what it says there, right here in this thing that you can't see anymore, but it says that right there. All right, the next one, let's do it blue. Okay, so these are the p's right here. Okay. Let's do the D's. Let's make them green. Okay, so the D's. Oops, sorry, my finger twitched. There we go. And the F's, and those are the ones on the very bottom. And I'll just go ahead and, that's the very bottom. We'll get them later. But these are your D's. Remember, D's is N-1. So that's what we want to remember. Okay, so if we're doing the electron configuration, I'm going to make that in red so that way there's no confusion as to what I'm writing. All right, so we're doing oxygen right here, this guy, right? And we have 8 electrons to place. So the first 2 are going to go 1 in the first S. So basically we have a 1, we have an S, and we can have 1 and 2 electrons in it. So that would be 2. See, that's the notation. We're saying it's level 1, orbital S, and it's in the second column. Okay, so helium really belongs, that's one thing that it's weird because helium actually belongs over here on this side, but it's put on the other side because it is a noble gas. So that's why he's way over there. Then we would have level, remember this is 1, this is 2, this is 3, 4, 5, 6, and 7, right? All right, so the next one is 2. So the next one is 2. And we got S1 and 2. So 2s2. If we stop right there, that would be the configuration for beryllium. Because every electron is contained in the one after it. So basically, every electron on the one before it is contained in the one after it. So in other words, what I'm saying is they're all part of each other. Okay, so the next one would be 2. We're still in 2. See, this is 2, and this was N, remember? So 2, and then that would be P, and we have 1, 2, 3, and 4. So 2p4. And that's how you do oxygen. So 1s2, 2s2, and 2p4. And we stopped it there because we reached our goal. Now, if we wanted sodium, let's say, okay, so let me erase that. So now we're going to sodium just to do something. Okay, so now we're going to sodium. We are now going to 2p6 because we're passing all of these. And sodium is on the next one, which would be 3s, but only 1 because sodium is right there. Come on, stop. Oh, sorry, this thing sometimes gets picky. There we go. Sodium right here, it's right there. See? So there's the 3s1. So it's level 3, right? So period 3, that's what that means. And the s orbitals, which is the first 2 columns, and only 1 electron in it, so it's in column 1. If you notice, one thing that I want you to pay attention, remember how I wrote down the maximum number of electrons? Okay, so if you count, there's 1, 2 for this one, right? 1, 2, 3, 4, 5, 6 on this one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 on this one. And 14 below. And so if we count it, it's 1, 2, 3, 4, 5, 6, 7. And by the way, 14 is here. This lanthanum is actually part of that up there. So 14 on that one. That's the F's. Okay. So you see, it does work. And if you ever forget the maximum, just count how many columns. That's all you need to do is count the column, because they're right there. They are doing their actual numbering themselves. Okay, so let's remove all these drawings. Oh, you know what's going to happen? It's going to, I don't want to do that. Okay, let me copy this guy. Select this guy again and copy it. I guess can I copy this? No, I cannot copy it. I think I can. I think they got a few new doctor. No. Okay. Save. Aha. Save as a PDF. There we go. All right, so I saved it. I don't know what I saved. I might have saved this whole mess, but okay. So let's clear all this. Hopefully that'll be it. If not, well, you know what. Okay, yeah. All right, so that's one. So now let's go back to the PowerPoint and look at it. Come on, PowerPoint. Oh, I hope if I did that. Okay. All right, so we are looking at oxygen again. If you're looking at your periodic table, which you need to be, because otherwise you'll get confused, we are looking at 1s2, and that's the orbital, remember? And this one is doing both the orbital diagram and the electron configuration will come later. So we're doing it backwards on this one. So the first 2 electrons go in there. Then we get another S, right? Because if you look at it, the way that it's written, it's like reading a book. If you're going from left to right and progressively 1 down, right? All right, so the next one is the 2s. And that one has another 2 electrons. And then you hit, if you go straight down, you hit that boron, carbon, nitrogen. Okay, all of those are the P's. And you always put 3 because P's are 3 orbitals, whether they're full or not. So 1, 2, 3, and 1 more is 4. And that's the whole thing right there. That's the whole electron configuration. You notice we accounted for 8 electrons. And we can say it's got a negative spin on the last one, or a positive or negative. It doesn't matter. That's what they call them, positive or negative spin. All right, so, and there's the actual electron configuration I wrote. Now you see where it came from. Okay. I don't know if I can maybe paste that thing in here, but I don't think so. Okay, so look at this one, sulfur. Okay, sulfur is going to have 16 electrons, so we got to do it again. So we're doing the 1s2 first. It's always the same. Then we got the 2s2 from boron, from lithium and beryllium. So follow along with me on the periodic table. Lithium through beryllium is 2s2. Then we got boron through neon, that would be 2p6. Then we've got sodium and magnesium, that would be 3s2. And then we've got aluminum, silicon, phosphorus, and sulfur. So that's 4 more, right? And we're still in level 3, so 3p4. Okay, so you notice they're different colors. The reason that is because there is a short form of this same configuration, and it uses a noble gas. And the noble gas it uses is what is known as the core electron. So the core electrons are represented by a noble gas only. You cannot put anything else. So a noble gas that is within the configuration, which in this case is neon. So we put neon in brackets. And then we just put the rest of it going down. Okay, so that's the shorthand. All right, so looking at the periodic table, let's look at how we did sulfur. So sulfur is 16 electrons. Okay, so without knowing where it is, we're going to land on it. Watch. All right, so we got 1s2. We know that because we know we're 1, 2, right? Then we got 3 and 4, so that would be 2s2. And we're just saying that S2 is full. See, we cannot add more because we said the maximum number of electrons for an S is 2. And we got 2p, 1, 2, 3, 4, 5, 6. So far we've only placed 10 electrons. That's not enough. We have 16 to place. All right, so we got 3s, 1, 2. Now we got 12. We know we're not going to make 16. We're not going to make all the way down to the end. So let's count 12, 13, 14, 15, 16. So that's 3p4. You see that? And that is where our sulfur is. Okay. So this is where I was telling you that it's interesting. So let me clear all of these. All right. Now, this is to remind you that we have that table being pretty much explained right now, okay? So watch. So we have the S region, right? The P region, the D region, which is N-1, we said that, and the F region, which is N-2. What does that mean? Okay. So just so that you remember that this 6, 7, oops. Okay, this 6, 7 goes with this 6, 7, right? So basically it fits right here in this area before the D's. So you go here, then you go here, and then you come back over, and then you go here, and then there. Okay, so that's kind of like a detour. You know how there's like footnote, not footnotes, but little, yeah, like a footnote to read before you get to the end. Okay, that's kind of what this is. You got to read this footnote first before you can go on to 5D. So basically, if you're reading a book, you're going left to right, bottom, then the next one, then the next one, then the next one, and so on. So this is kind of how we're doing this. This is the same direction that we're traveling in this one when we're doing electron configurations. Okay, so let me clear all of that. So again, S is N, right? It never changes. So if we're in 1, you notice the S's are 1, 2, 3, 4, 5, 6, 7, 8, 7. Okay. The P's also, but there's no 2p because there is, remember the first orbital can only hold 2 electrons. Therefore, the P's are not included. All right. So, but we still got level 1, 2, 3, 4, 5, 6, and 7, right? All right, so the 2p's are all of these, see? And there it goes with the number, see? But you notice that this one right here, right, is an N. But then this one, the D, is an N-1 because we're in level 4, -1 is 3. You see that? Okay, and then here, level 5 -1 is 4. Level 6 -1 is 5. Level 7 -1 is 6. Okay, now let's look at the next one. 6, look at who's coming next. After this 6, you would actually go here. Okay, so after 6s, so 6f. but it's not 6F because it's N minus 2. So 6 minus 2 is 4. And 7, right? Because that's this one, minus 2 is 5. And that's the only two that.
What does
Yes, ma'am?
what does N stand for?
N, it's just a coefficient,
Yeah.
basically the number that's before the letter.
Okay.
And N represents the period number, these, right?
Got it. Okay. I understand.
Okay. All right. So just, I know it's complicated, but once you get it, it's like, oh, it's so easy, you know? You'll see. Believe me. It's not that bad. I wish I'd have known this part when I was doing mine. I could tell you horror stories, but I'm not. I'm just being silly. Okay, so an example is hydrogen. Okay, so we know that hydrogen is where that blue square is. So hydrogen is in level 1, so we put a 1. In the s orbitals, which are the yellow part, right? Those are all s's, but there's only one electron, so we just put a 1. So that's all that means. Every time that you see this notation, this is what it's telling you. That's the period, that's the block, and that's the first column. That's where to locate it. Now, if you're actually interpreting it a little different, like about the electron itself, the electron is located in level 1 in an s orbital, and there's only 1, so that means that it's pointing up. You see that? That's basically all that's telling you. So if you were to draw that into a little box, or I don't do boxes, like I said, I do lines. So if this was hydrogen, this is what I would draw. See? That's it. That's all of it. That's what it told me to do right here. This is telling me everything to do for the diagram. This is the orbital diagram right here, and this is what is known as the electron configuration. Okay, so let me clear all of these and let's keep going. All right, so let's do another one. Okay, so another thing is a lot of people don't realize. Okay, so if we're doing the shorthand, which for hydrogen, there is no shorthand because there's nothing smaller than hydrogen, then what you need to do, and see, this is, once you see this, it makes more sense, doesn't it? How to follow it. Once you see this, because you can see that the 6 goes from 6s, oops, sorry, back. I don't like it when that happens. Okay, come on. There we go. All right, let me go back to my little drawing. Okay, so let's say we're following this path right here. So we go 6s. Remember, we're still in 6, but it's n minus 2 now. So it's 4f. Then we're still on 6, but now it's n minus 1. So it's 5d. We're still on 6, so now it's 6p. You see that? That's the path we're following right there. If we're doing the bottom one, same thing. So 7s, 5f, 6d, and 7p. You see that? Even though the p's aren't there, but guess what? They are there now. So this is an old PowerPoint, but they are there. All of this is there now. So this whole entire periodic table is full now. All right, so let's clear all of that. But it makes more sense why the detour, because this is really what the periodic table should look like. It's just that we cut that bottom out, because can you imagine how long it would be if we didn't? And you couldn't even read the information in it if I gave you a periodic table that was whole like that. So anyway, let's keep going. All right, so read the directions. Okay, so you represent the core electrons by a noble gas. So you go up one row and all the way across to the noble gas, which means all the way to the end of the periodic table. And then write that down in brackets. And then on the next row, you will fill all the electrons that are left. Okay, so let's see what that's saying. Okay, let's go there. Okay, so let's do germanium. Okay, so germanium's right there. Okay, so the rules say go up one row. So let's do that. Okay, so germanium, you located it. You went up one row. What noble gas is that?
Is that neon?
No, too far. That's one too high. Look at where germanium is. Look for your germanium on your periodic table. You go up one row, just one, not two, and then go all the way across to the noble gases. And that's the third noble gas down. So that would be which one? Okay, I'll give it to you since you're all being shy today. It's argon. Okay, so now we haven't gotten to germanium yet, right? We're just right there in that pink little square. Okay, so now we need to get to germanium. So we need to go to those and we write that down. So that would be 4s2. And then we go all the way across these D's. And remember, D is n minus 1 and we're in 4. So that would be 3D. And we said the maximum, which is where we are at because we're past it. So 3D10. And then 4p12. See? And that's your whole noble gas 1. Now, if you were to write the whole entire configuration, you would have to write all the beginning too. So there's a long form and there's a short form. And the short form focuses on what is known as the valence electrons, which is all we really need to know when we're doing reactions. Because the only the only electrons that react are the valence electrons, which are the electrons on the outer shells. All right, so let's keep going. All right, now stability-wise, we have different things that we need to know. So remember how everybody wants to look like a noble gas to be stable? That's
Yes. Okay.
that is when you have a full energy level. Remember, I keep saying it. They're full, they don't want anymore. Okay, that's what that means. That's the most stable. The next one is a full sublevel. So a full S, a full P, a full P no, because full P is full, and a full F. So a full D, an S, or an F. That's more stable. The next one is a half full sublevel. And not the S's, because the S's, there's only 2. So half full, it's not really stable. Okay, but right here, the middle ground of the D, so D5, the middle ground of the P, so P3, and the middle ground of the F's, or F7. So all of those are more stable. And then random order, it's the least stable, okay? Now, these are your exceptions. Remember, I told you there would be some exceptions. So copper is number 1 exception that we have. You would expect if you were doing this electron configuration. Okay, so if we go back to, let me go back to the periodic table so that we can look at copper. Oops, sorry. Did not mean to do that. Meant to escape this so I can go back to this. There we go. There we go. All right, so copper is right here, right? Let me see. Let me annotate, highlight you. There we go. Copper is right here. All right. And we said go up 1 and go across and pick that one, right? All right. So and I'm just going to write it. I'm going to write it with my finger because otherwise I cannot do the S2 above like it's supposed to be. So we're going to start with argon. Okay. Now, we have to get to copper. So we got 1, 2 on the S's. And what level are we? 1, 2, 3, 4. So it's 4S and 2, right? And then we got all of these. 1, 2, 3, 4, 5, 6, 7, 8, 9. And that would be 3, remember, because this is n minus 1, D9. That's what you would expect. But look at 3D9. Isn't that like 1 away from being full? Because, you know, all the yellow, right, would be gone. So what it does is it borrows an electron from here, brings it over here. So the actual configuration for copper for stability purposes is 4s1 3d10. And yes, it is breaking that rule. Remember, I told you there are a few exceptions to not Pauli's, but Hund's rule. Hund's rule is broken right here. It has to be because of stability. Now, you're thinking, well, what's the difference between it and zinc now? Well, zinc would actually have the S2. This would be the difference between zinc and copper. See? Because it actually has 12 electrons on that level. So it has 1 more. And that's the thing that we're talking about. It is important to know that. Okay, so let's clear all of these and go back to our PowerPoint again. All right, so here we go. So like I said, you would expect that, but it's if you did your electron configuration, but it's not. What it does is it borrows and it becomes this. And that offers copper stability. You notice copper doesn't rust. Copper doesn't react much. That's because it's stable. Copper is one of the least reactive metals. Okay, all right. So chromium is another exception. Let's go back to the periodic table and look at that one. Okay, so chromium happens to be on the same row, but it's right here. Okay, so chromium, again, we do the same. Oops, what in the world? I did not want you to go away. Look at this thing. Okay, this is annoying me. Let's just do this one then. All right, chromium. Will you stay now? Okay, so we said 1 up, go all the way across to the noble gas. That's argon again. Okay, so we write it. We write what we know. Okay, so we know that it's supposed to be argon. And then we got 4, and this was 1, 2, 3, 4, right? So 4s2, and then 3d1, 2, 3, 4. Again, what do we know about stability? We know that a half-full sublevel is also more stable than what this is, than this configuration that we have here. So what it'll do, it'll switch one of the s electrons, so it'll become 4s1 and 3d5. And chromium, as you also know, does not rust because it has this wonderful configuration that makes it more stable. So that's why it does that, for stability purposes. All right, let's go back to clear and go back to our PowerPoint. All right, so this is chromium right here. That's what you would expect, but this is the reality. And not all of them do that, by the way, but most of the ones that are in those middle grounds kind of do. And there's some that do other weird stuff out of the blue for no reason at all, but it happens. But, you know, we'll look at those later. But this is how it works. So this is the whole entire thing. Now, let's go back to the periodicity PowerPoint because that one actually is pretty good. Let me go back to it. Okay, so I wish I could open both of them at the same time, but I can't. I cannot have them open. Okay, so periodicity has a little bit on this too, so I wanted to go back to it. And we're going to go back to opening the periodic table again. Now that I've got that one open. Okay, periodic table, where are you? There we go. All right, let's open. There we go. Just leave it open for now. All right, so here we go. Periodicity. All right, so we had, remember, we skipped this, but there's a reason we skip it. I think it's easier to learn about it afterwards than before. All right, so when you're looking at this, it's the same thing. See, but this one actually gives you arrows, so I love this one. It's like a roadmap. So if you want to take a picture of this one, I would. This is probably the best one that helps you figure out. See how it even gives you go to 5D, go to 6D. And it gives you the coefficient already there. So you got it? All right, so next we're looking at electron configuration again. And this is just a shortcut part, but we're learning the long. You can't run unless you learn to walk. So we're walking by doing the long form first, like phosphorus, for example. Okay, so phosphorus has 15 electrons we must place. The first two go in the S, right? The second two were in another S. So 1s2, 2s2, that's 4. Then we got 2p6, that's 10. 3s2, that is 12. And we have 3 left, and they go in the 3p3. And we set to go up one level and go across to the noble gas. That gives us neon. And then we just go all the way across from neon to the phosphorus. And that would be 3s2, 3p3. And that's how you do a shortcut configuration from a long form. It has to be a noble gas. You can't just put anything there because noble gases are 100% full, and that's what the core is. All right, so let's do these. All right, I want you to find barium on the periodic table. I can even give you its number. It's 56. So you can find it faster. Go up one level, go all the way to the period from on the periodic table all the way across to the noble gas. What noble gas is that? And if you can't talk, you can put on the chat because I want your answers. What do you see? Which element is that? So remember, locate barium, which is element 56. Go up one row, go all the way to the end, to the noble gas. Which one is that? Okay. Looks like I'm going to have to find a periodic table for you. All right. So here we go. Again, directions. Locate barium. We are locating barium right here. Barium is element 56. Go up one row, go all the way across. Notice how I'm going all the way across to the noble gas. There it is, xenon. Now write that as your core. Oops, what in the world? This thing sometimes. Write that as your core. So xenon in brackets, right? And then get to barium. So this is 1, 2, 3, 4, 5, 6, and 7. Okay, so barium is in 6, right? And it's on the S, and it's 2. And there you go. That's barium right there. That was pretty easy, wasn't it? All right. The next one that I think we had was mercury. Let me see real quick. Oh, come on. Do this. Yeah, it is mercury and then vanadium. Okay, so let's go back. Oh, sorry. Sometimes this thing annoys me. Okay, barium. Okay, so then we got mercury. All right, mercury, we located. It's right here. Oops, I forgot to bring down. And let's make it a different color just to have a different color for mercury. So mercury is right here. Up, noble gas, still xenon. Okay, so mercury is going to be xenon. And we have xenon, and we got 6s2. We have to get to it, so we got to go all the way across. From 6, we got to go down to these guys, and that is 4f14, because all of those are full. Then we go back up again, and we go all the way across to mercury, which looks like 5d10. And there's the electron configuration for xenon. And the last one was vanadium. Let's make that one green, just to have a different color. Okay, so vanadium is right here. Okay, vanadium is right here. Up, noble gas. Oops, sorry. That was my finger twitching again. It's argon. So this time we write argon. And we find out where vanadium is. Okay, so we got 4s. No, sorry. Yeah, that is 4. 1, 2, 3. Okay, that 3 should be here, and that 4 should be here. Yeah, so that is 4. Argon 4s2. And vanadium is 1, 2, 3. So 3d3. And there you go. And that's all of them. So let's go look at how we did that. Let's clear all of these and go to the PowerPoint again, so we can see it in action. Okay, so again, barium, we said it was xenon, and then we went all the way across to barium, which is 6s2, and that's it. Mercury, we located it, it's also xenon, and it was 6s2, and we got to go down to the F's, 4f14, because it's full, and then 5d10, and there's mercury. Vanadium, we located it and looked for the noble gas, seems to be argon. And then we got 4s2 and 2 vanadium. There's 3 into the D, so it's 3d3. And that's it. All right, so on this periodic table, if you could actually see it very well, every single one of the elements has its short-term configuration. Short form, I mean, configuration. Do you see it? Every single one. There's manganese. See, you can kind of see them all. See? Cobalt. There's the exception. See how it's got 4s1? They put them in order, which I hate that, because the order of filling is not the order that they're written on here, which kind of gets confusing to a lot of people, and so I don't like it, but it is what it is. It's all we got. So with let's see, you were wondering if chromium, molybdenum, and all of them. See, they do, but okay, so chromium does. See, it's got the 1. This one's got the 1. This one does not. This one does not either. Okay. And then the last one was nickel copper. Hello, copper. Here we go. It's got the 1. This one's got the, see, this one's got the 1 also. This one does too. And so does this one. So it's hard to know whether you're going to do that adjustment or not. Look at gold. Gold's got the 1 also. But gold is not 100% full, which is weird because we don't know why it does it, but it does it. So does uranium over here. It does the UUU. Sorry, UUU has the S1. It's weird. I know. It's just the way they do. Sometimes it's for a reason, and sometimes it's just probably because they're so close. They're so close in energy, the levels, that they just jump up and down. I'm guessing. I don't know why otherwise than that. Okay, so that's electron configuration for you, and we can do a little practice. Okay, so I think that was it for this one. Yeah, that's just to show you the configuration itself. And this one always puts it on cobalt. I don't know why it moves it to that one when it should be on copper. I always escape it and move it down so you guys can actually see the right one. Okay. I need to edit. Oh, that's okay. Yeah, I know. Okay, so bring you down. Stupid thing. There we go. It needs to be on copper. There we go. I don't know why it does it on cobalt. And then bring this arrow down a little bit. There we go. Now we can look at it properly. And then, okay. All right, so now chromium is an exception, and so is copper. See? There they are. Because they're more stable that way. Okay. Okay, we already saw this. Okay, so yeah, we did that. All right, so now let's do some practice. So for this part, we will need a sheet that is, let's see, where are you? I need to get out of this one. Yep, go back and get the sheet. Okay, the sheet is called Electron Configuration Practice. And it also does orbital diagrams right here. And this is what I was telling you. I don't do the long thing. I just do the lines. The lines are easier to do when you're trying to write something like this, and it's hard to write it in here to begin with. Okay, so why do we do this? All right, so we need to know the number of electrons so that we can actually confirm it. How do we confirm? Add every single one of the superscripts on the electron configuration. So basically what we're doing is we're adding 2 plus 2 plus 6 is 10, plus 3 more is 13. And look, this is how many electrons we had. Now, the period that, the period that aluminum is found on, which tells us how many electron levels there are. You notice that we got the 1, the 2s, and the 3s. So this whole, one of the things that people don't want to remember is that 3 means 3. So when we say level 3, we're talking about all of those, okay? So you notice electron levels is period 3, right? Because this number right here is 3. And so is this one. So that's the last of it. That's the outer layer. Now, counting the electrons, we have 1, and here we have 2. So for a total of 3, and that's why we're in group 3A. You see that? That works beautifully. This periodic table was genius, you know, when they did it. Now I'm going to go ahead and type in the numbers that are in here. I think I can. Yeah. All right. So this one's going to be 12. Ooh, well, maybe not. Maybe it's not letting me. Why it's not letting me? I need 12. Okay. Let's see. Well, there we go. Okay. What period are we in on magnesium? We're in period 3. Oops. Why is it not letting me type? This is annoying. And what valence? Okay, it's 2A, right? Oh, come on. Every time I have to click. Yeah, 2A. Ah, that's probably because it's already there. All right, now this one, the electron configuration, I'm just going to write it without going superscript on it. So it's 1S2. And if you can't read it, that's fine. Okay, let's find it. Yeah, that's the problem. It's already here. Now this one I can't give you, but this one right here, oh, we didn't do this one. Let's do this one first. All right, so the noble gas, again, you got to look for the noble gas that is on aluminum. That would be neon in this case, right? It's above aluminum, so 1 over. And then you just bring down the rest, which is 3s2 and 3p1. And that puts you these last ones right here. See these right here? Oh, sorry. Highlight. There we go. These right here. That's what it's telling you. Those are this right here. All of this entire thing I'm circling. This is neon. All right. So the next one is magnesium. And we got neon again, right? Because it is in the same level. Oh, yeah. Okay. So now it's right. Okay. So neon. Capital N. Okay, neon, and we got 3s2, and that's where it ends. So if we were to write it, I'm not going to write the whole thing. I'm just going to write the last 2, okay? Because otherwise we'll be here forever. And so basically it's all of these, right? That's your neon, so we know that's in common. But then we got just this one. That's the ending of it, right? That's it. Then the next one is silicon. All right, so silicon is 1 over after aluminum. So this is going to be 14. 14, right? And this one right here is period 3 again. But the group is going to change. It's going to be 4A. Right? So what does our electron configuration look like? This right here. Okay, see? All right, and again, if we were to take our annotation and look at where neon stops, it would be right here. This is neon right there. So what we need to write down for the electron configuration is neon. And the next part would be 3s2. And like I said, I'm not going up on this one, but that's okay. And 3p2, right? Because it's 4 of them, right? So if we were to write down all of the electron configuration, remember that part that I circled, that's neon, so that's common to everybody. So in this case, it would just be 3. Okay, so it would just be 3s2, and that's still 3s right here. And it would be 3p. So remember, there's 3 for that one. So all of these are your 3p, and it's 2. So 1 and 2. See, just got a positive spin on the last one. All right, titanium. Titanium is what element? 22. So we are one up on this one. Okay, we're one down, I mean. So we're 22 electrons. We're in 4. We're in group B because titanium happens to be a transition metal, and all the B's are transition metals. And here's your electron configuration normally. Okay, so how do we do our shortcut? Okay, so look for titanium, go up 1, and that is argon. So AR, right? And then that is going to be, so where does titanium start? Well, I mean, this right here. Oops, come on, let me annotate. Okay, right here. This right here, all of this is argon. Okay, so we now need to finish this, and that would be 4s2 and 3d2. So if we were to write down just the outer part of this, and I know there's a lot more to go, but 3p, you can imagine that's 6. So now we've got just the outer part of this part. Okay, so that would be 4s2, and we got 3d. So 1, 2, 3, 4, 5, because this is a d. So 4s, this is 4s right here, and 3d2 is just 1, 2. That's it. And that's all your 3Ds. And I know I'm getting into each other's. Like I said, this is hard to do when you're trying to do this particular thing. Okay, so next one is nitrogen. Now we're moving up again. All right, we're not going as an, all in one area. No, we're not. We're just doing one at a time. So this is 7. That's how many there are. There's period is 2. So this time, nitrogen is in group 5A. And this is its electron configuration, the long form. This is very long, short form. All right, so what would be its shortcut? Okay, well, it's not much of a shortcut, but it's helium, right? Because we're going nitrogen up 1, and there's helium. And then it would be, and helium is just this part right here. Oh, come on, give me a notation. Okay, right here. That's helium. So then the rest of it needs to be written there. And that would be 2s2 and 2p2. 3, not 2. Okay, so to write that down, that would be, and this is the hard part, trying to get it all to so that it looks small and good enough and all that. It's not easy. Okay, so this is 2s and this is 2p. Remember, 2p has 3 orbitals, so 2s is full, right? And 2p has 3. 1, 2, 3. That is that other principle that we need to not put in until we can double, right? That's Hund's rule again. All right, potassium, now we're going up again. Potassium is a larger one. We got 19 electrons to put in. So 19 electrons in period 4, group 1A. And we are ending in S1, obviously, but we don't know. Okay, so what is our noble gas? For potassium is argon again, right? Oops, sorry. Argon, okay, and it is just 4s1. So very short. So all we need to draw now is just the S1. That's it. That's a 4. I know it's hard to close it. All right, and that's those. Now we got one last one, and I'm going to have to clear everything here, all the drawings, so that I can actually get to it. All right, the last one we are doing is this one, copper. Okay, copper. Remember, that's our exception. Oh, copper. I say chromium. Chromium has 24. It is in period 4. It is in 6B. All right. And this is its long form configuration right here. Okay. And we know that it's an exception. So we are now doing and we never did kind of show you where argon was on that one, but I think you're getting that is the P6, right? That's argon, and so is here. So basically all we have to write down is whatever's after that. Makes life easy when you have a long form and you're doing a short form. All right, so chromium is argon, oops, capital A, R. And then we have 4s1, defying Hund's rule, and 3d5. All right, and that's that.
I have a question.
Yes.
How do you know which electron to borrow on this one?
Oh, it's always the S going to the D, because the actual, let me show you what the actual configuration would be. And I'm going to do it on the electron configuration part, on this part right here. So this, ooh, hold on, I need 5 of those. I cannot make them that big. I will never get them. Let me just get them clear all. Okay, there we go. Do it again. All right, so again, this is S, 1, 2, 3, 4, 5. Okay, so basically, if you were this guy, this is what normally, okay, you would be like this. Isn't it easy to know which one to borrow now? Well, you can borrow from anywhere else. So where can you borrow from to make it 5? This guy.
Oh.
See? And so it's S1.
So that would make it.
See?
That would make it.
Mm-hmm. That would make it half full, which is more stable. Mm-hmm.
1, 2, 3, 4, 5.
Yep.
Okay, I see it now.
It's still the same 6, okay? It's just in a different area. They just move that 1 over. That's it. And if you look at the diagram that I showed you at the very beginning, there's very little difference between those, the S and the Ds. And that's why they can jump. And that's why we have transition metals, by the way. That's why we have all these double, like chromium can have a 3. Let's see, chromium, if I'm not mistaken, is a +2 and a +3. So the +2 would be this guy and this guy, right? And +3 takes one more of those.
Yes.
Yeah. So that would be the 3 that would get lost. So basically you would lose all your S's. Because that's,
And there's only like 5 that's like that.
Yeah, there's only a few.
One more question. I don't know if you already answered this. These are not ions. It's just simply the elements.
These are just the element. Yeah, these are electron configuration of atoms. No, we'll do ions later. Yeah, the ions is.
Oh, good.
Yeah, we will be doing ions later. She's like, it's not sarcasm.
Okay.
I'm just kidding. Yeah, we will be doing more of those later. But the thing is that these right here, here, let me do the spotlight, because this is what makes it easier. These right here, right, are actually very much like these. That's all it is. It's just you have to remember how many lines to put for each one. That's all.
Yes.
And the reason is that's why I gave you that table at the beginning, orbital wise. So if I asked you, and this would be a trick question, how many electrons can a 5D orbital hold? And you're thinking, oh, it's 5D. Oh, so you would think it's all this. No, the word is D. D is 5. 5 orbitals, 10 electrons. That's it. No more than. You see?
I think I understand that.
Yeah. So, I mean, it doesn't matter what is put in front of it, as long as it's a D, it can hold up to 10 because you got 5 little lines, and the lines represent each orbital. And that's the main thing about that, is that if you realize that, that makes your life a little easier. And we'll do some more. I'm sure you'll have some on your Connect, which is open right now. And you should, let's see, I think that's chapter 7 that we're doing. Yeah, we're doing chapter 7 right now.
Okay.
And there are some questions about it there.
Once I get the hang of this, it's going to be fun.
Yeah, it's actually pretty easy. You just gotta, I mean, one of the times that I and that we'll start with that next time, is I'll do platinum for you, and I'll do the whole thing, and you'll be going, oh my God, that's forever. But it is necessary for you to comprehend it. It is one of those things. Or I'll
Yes.
just ask you for one of them that are in the lower, in the, either from 70 on down, any of those. Then I can do those for you, and you will see a difference, because one at a time is best too, so that you can actually see where everything's coming from. Ready. So that's all I had for today. And I'm going to go
All
ahead
right. Well,
and,
thank you so much.
oh, you're welcome. I'm going to go ahead and end this now, and I will put it on later, the recording.
All right. Thank you so
Okay.
much.
Thank you.
Have a good day.
You too. Bye-bye.
Bye bye.